Swayamprabha. Digital India. Educated India.
In the previous lecture, we derived the Navier-Stokes equation, and towards the end we made a conclusion, we arrived at a conclusion that there are situations when you require to solve the Navier-Stokes equation in conjunction with the energy equation. I mean, one example that we cited to establish that fact is that when density is a function of temperature and pressure, but I mean there are several other considerations when you may not relate density as a function of pressure and temperature through equation of state, but the sensitivity of density with temperature is just given in terms of a volumetric expansion coefficient, which comes into the picture by creating a density gradient due to temperature gradient that drives the flow, and that is called as natural convection or free convection. So, there are various possibilities when in which the energy and the Navier-Stokes equation they need to be dealt with together. So, there are situations when they are coupled, there are situations when they are not coupled. For example, in a heat transfer problem in which rho is a constant, then you can solve the Navier-Stokes equation separately, use that velocity field in the energy equation to solve for the temperature field. But if rho is a variable, then you have to consider them coupled. So, these are various possibilities. Now, we will move on to the solution of the I mean the derivation of the energy equation. So, to do that we will use the Reynolds transport theorem. In the Reynolds transport theorem, now capital N is the total energy, which is the summation of internal energy, kinetic energy and potential energy. That is what we consider in thermodynamics. In classical thermodynamics, we consider all forms of energy other than kinetic and potential energy, we club that together and give it a name internal energy. So, internal energy. So, just in thermodynamics books, so here we just use a little bit of different notation as compared to the thermodynamics books. In thermodynamics books the internal energy is given by U, but we are already using U for velocity. So, we are considering I as the kinetic the internal energy per unit mass, just a notational difference, but otherwise these are very familiar forms of energy that you know from thermodynamic considerations. Small n is capital N per unit mass. So, small n is what? Small n is I plus V square by 2 plus Gz. Okay. So, now the Reynolds transport theorem, if we use n as capital E, the total energy of the system, then this is dE dt of the system. So, dE dt of the system is what? dE dt of the system is nothing but the change within the control volume. So, the del T integral of rho E dV plus the outflow minus inflow rho E V dot dA. V dot dA is actually V dot eta into dA as scalar, where eta is the unit normal vector. So, you are by this time very familiar with these types of terms, and we are just going to use those here. So, now under conditions of non deformable control volume, you can take this del T out of the derivative, and for stationary control volume the relative velocity is same as the absolute velocity, the velocity that you have used here, and you can convert this area integral into volume integral by using the divergence theorem. So, you will get this particular form, right. So, in place of E V dot dA, it is divergence of EV, divergence or sorry, rho is there. So, rho E V dot dA is divergence of rho E V. So, divergence of rho E V is del del xj of rho E uj. Okay. So, that is what is written here. Now, you can see that, so d dt of the system can be written as, the right hand side can be simplified further. So, this is what form, conservative or non conservative? This is the conservative form. Remember, we can always convert the conservative form to the non conservative form by using the continuity equation. So, that is what we are doing in the next step. So, what we are doing, you have rho into del E del t. So, del del t of rho E is what? Rho del E del t plus E del rho del t, these two terms. Then del del xj of rho E uj, rho uj into del E del xj plus E into del del xj of rho uj, just like what we did for the Navier-Stokes equation, very similar. And then you can see that these two terms, they combine together become 0, because that is nothing but the continuity equation. So, you will get rho into del E del t plus uj del E del xj. What is this? This is the total derivative of E, right. So, rho dE dt, the total derivative of V is acceleration, the total derivative of d is just total derivative of E, we do not have any special name associated with that. So, the right hand side is the rho into total derivative of E dV, and the left hand side is dE dt of the system. So, in the next slide we will see how do we relate the dE dt of the system with heat transfer and work done, and for that we relate that with the first law of thermodynamics. So, let us go to the board a little bit to understand the background. So, let us say you have a control volume. The first law for a system, so first let us consider this as a system. Why we have written it in terms of the system? Because first law is traditionally defined for a system. In fact, the first law is traditionally defined for a system undergoing a cyclic process, that is the cyclic integral of heat is proportional to the cyclic integral of work, but that can be converted to a law that governs for a system undergoing any process, need not be a cyclic process. So, for that we have the positive sign convention that we commonly follow is heat transfer to the system, that is considered to be positive, and work done by the system, that is considered to be positive. Okay. So, energy entering the system in the form of heat is positive, energy leaving the system in the form of work is positive work. So, what we can write here is so, this is just an energy balance basically. Say let us say you transfer some heat to the system. So, what will the system do with that heat? It will do some work. If it does not do some work, the remaining part will change the, simply increase the energy of the system, right. So, that is a basic energy balance. You give some heat to the system, it can use the part of the heat to do work, the remaining part will increase the energy of the system itself. So, that is what it is, and this d, if you consider transport, this is actually meaning total derivative, this d dt, because it is about the system. So, the total change because of transport and everything change with respect to time, everything is considered within it. So, you can see that d dt of the system you have to remember that it is not a must to take this sign convention. You could have taken a different sign convention for work and then simply this will become plus instead of minus, nothing more than that. Okay. So, the next step is that remember that while deriving the Reynolds transport theorem, we took a limit as delta t tends to 0, so that the system is tending to the control volume. Therefore, this for the system is as good as this for the control volume. Okay. So, these are the thermodynamic parameters with which we are relating to the d dt of the system, and these parameters we will write in terms of the transport. So, let us try to do that now. So, q dot Cv, what is the rate of heat transfer? Now, just like in continuum mechanics, in force you have surface force and body force. Similarly, heat transfer, volumetric heat transfer and surface heat transfer. So, volumetric heat transfer, let us say that q triple prime is the rate of heat generation within a volume per unit volume. So, for the volumetric term, this is this, very simple. This is q triple prime is per unit volume, you multiply it with dV and integrate it over the control volume. Okay. What about the surface term? The surface term is given by what? Surface term is given by heat flux. In heat transfer, whatever is the, so let us say this is the control volume. Let us say there is a heat flux q, typically q double prime we consider as heat flux and triple prime as volumetric heat generation, that is the standard notation that we follow. So, q double prime, let us say this is a small area dA. So, q double prime, which is called as the heat flux vector dot eta dA is the rate of heat transfer through dA. What is this eta? This eta is a unit normal vector. So, we can integrate this, but we have to keep in mind one thing. Here positive heat flux is in this direction, but by the sign convention that we are using in first law of thermodynamics, positive heat transfer is heat transfer to the system or to the control volume. To adjust for that, we use a negative sign here. So, minus integral of so what is this? Minus integral of divergence of, this is control surface, using the divergence theorem. So, this in a shorthand notation, this is what? Index notation del qj del xj. Okay. Now, this is about the heat transfer. What about the work done? W dot Cv. for work done, what are the forces that we are considering? Surface force and body force. So, first let us write the body force. I am not commenting about the algebraic sign, the algebraic sign we will discuss later on, but first let us write the contributions. So, let us first write for the body force, it is more trivial. So, body force is what? Bi into dV is a, if you take a volume element dV, then the force acting in the ith direction is Bi dV, and work done is what? Dot product of the rate of work done is dot product of force and velocity, right. So, Bi into Ui, this is basically B dot V, right. So, Bi Ui dV. So, for surface force is given by the traction vector. So, plus Ti Ui dA. In one of our previous lectures, we have discussed that this is nothing but the vector tau dot eta, where what is this tau? Tau I1 I plus tau I2 j plus tau I3 k, right. So, in terms of the divergence theorem, what it is? Integral of divergence of what? This is control surface, this is control volume. Control surface divergence of, it is not visible, I think computer is blocking it, so write it separately. Write it here. So, tau I that is del del xj of tau ij ui, okay, dV, integral and all those things. So, we have represented all terms in heat transfer and work in terms of volume integral. Only thing which we have not yet done appropriate is the algebraic sign of this WCV. So, why it is so? Because here we have considered work done by a force as positive work, but in thermodynamics positive work is done by a system when it does work against a force, that is a it overcomes a resistance. A thermodynamic work is what? That you have a resistance, you overcome the resistance to do some work. So, that means that is what is positive work, that is why energy leaves the system, because you have to overcome the resistance to do the work, and work done by the force is just having an opposite thing. So, to make up for that, actually you have to put a minus sign here, I mean either in the left hand side or in the right hand side. So, if you take care of all these, so let us see that, let us get back to the slides to summarize what we have learnt by now. First law of thermodynamics, then the expression for heat transfer and work done, and of course with a positive like the positive sign convention as per the standard consideration that we have in thermodynamic textbooks. So, these expressions we have just now derived. Now, if you now these expressions you can see left hand side and right hand side, you have left hand side you have in one side, right or left is up to you. So, rho into d dt dv integral of that is equal to the heat transfer and work done dv equal to 0. So, that means because your choice of the control volume is arbitrary, this is what you get straightforward from the previous expression. So, this is the rate of change of energy term, this is the heat transfer term, this is the work term. Okay. So, we will take it up from here. Now, this is what? This is conservation of what? This is conservation of the total energy of the system, but in heat transfer we are mainly interested in the conservation of the energy in its thermal form. That means we are basically talking about the internal energy. So, we must sort of subtract the kinetic energy conservation from here to get the energy conservation in terms of internal energy. So, that we will do. Let us go to the board to do that. So, to get the kinetic energy equation, we start with the Navier's equation. See, at this stage we do not give a specific emphasis to whether the fluid is Newtonian, Stokesian, all those things. We start with the general equation of motion. So, we have rho dui dt that is equal to del tau ij del xj plus bi. Okay. So, what we do is we multiply this with ui. So, you have rho d dt of ui square by 2. Right, and then this is ui del tau ij del xj plus ui bi. What was our total energy equation? Let us write at the top, rho d E dt is equal to q triple prime minus del qj del xj plus bi ui plus del del xj of tau ij ui. Now, we subtract this equation from this equation. If we do that, you have rho d dt. See, what we are claiming is that if